Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about nuclear reactions and kind of why they occur. Now, the reason why nuclear reactions occur is because they have an unstable nucleus. And this happens with what we call radioisotopes. And radioisotopes are just basically radioactive isotopes. And the word radioactive just simply means unstable. So we have these radioisotopes with a nucleus that's unstable, and it's unstable for three different reasons. Okay, the first reason is could have too many protons. Second reason is the proton to neutron ratio might be off, different than what's on the periodic table. And then finally, the nucleus might just have too much energy. And based on these conditions, okay, you're going to have different types of nuclear reactions that occur. Okay, so let's talk about the first one, having too many protons. And when we say too many protons, we're talking about having more than 83 protons. So that's a lot of protons in a nucleus, okay? And what I have here is an example of just a nucleus because we're talking about nuclear chemistry and nuclear reactions. So we're talking about the chemistry that happens inside the nucleus, where the blue circles are going to be my protons and my red circles are going to be my neutrons. And I don't know if you ever wondered, it's like, how do these protons get close to each other? Because you remember, when we're talking about the size of the atom, the nucleus is really, really small relative to the size of, the entire atom. The analogy that I use, I live here in Cincinnati, so we talk about Paul Brown Stadium, which is now Paycor Stadium. It's where the Cincinnati Bengals play football. And we said, hey, if the atom was the entire stadium, which is super huge, okay, the nucleus would be like a marble on the 50-yard line. Okay, so as far as like perspective here, the nucleus is really, really small. So I've kind of blown it up here on the board a little bit, but all of these protons and neutrons are going to be packed into this tiny little place called the nucleus. And I'm wondering, well, I know protons have a positive charge, and this proton has a positive charge. How do they get close to each other? Okay, because according to Coulomb's law tells us that like particles want to repel. It's only the opposite charges that attract each other. And inside the nucleus, we have neutrons which have no charge, okay? And the only other particle are protons. And how do they get close to each other, okay? Because they're really trying to get away from each other. So if we took a look at maybe these two guys here, they're trying to get away from each other, okay, because of Coulombic forces, okay, the like charges repelling each other forces, okay. So there's another force that's coming in that's holding everything together that's actually stronger, okay, and those are going to be called our nuclear forces, okay. So you have these nuclear forces that are stronger than the electrostatic or the Coulombic forces that are trying to get protons away from each other. The nuclear forces are going to say, no, 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 you guys need to be tightly packed in here. So these guys are stronger than the Coulombic forces that are trying to push them away. Well, until you get to a certain point, okay? So if I start to load up more protons in this nucleus, okay, oh my gosh, these guys are really starting to repel each other. There becomes a breaking point where these nuclear forces just can't hold those protons together, okay? And that limit in chemistry we found out to be 83. So when we look at the periodic table, bismuth is at atomic number 83, 84 would be polonium, and as soon as you get to polonium, we're saying that that's radioactive, where we have an unstable nucleus, because the nuclear forces just can't hold those protons together because they're trying to repel each other. So that's kind of the story of having too many protons, where the Coulombic forces overcome the nuclear forces. And the question is, well, what happens in that situation? Okay, so let me erase my nice drawing here of my nucleus, and let's take an investigation on uranium-238 as an isotope, okay? Now, it has an atomic number of 92, so that means that there's 92 protons in this nucleus, which puts us in this category of, hey, that's too much, okay? The nuclear forces can't hold those protons together, Okay, so what happens is part of this nucleus comes off, and it comes off in terms of what we call an alpha particle. Now I have some common particles over here. These are the protons, neutrons, and electrons. And if you look, the top number is the mass, and then the bottom number is the charge. So a proton has a mass of 1 and a charge of 1. A neutron has a mass of 1 but no charge. An electron has no mass but a charge of -1. And then we got some other particles that are up here that are going to be used later in some of our other nuclear reactions, an alpha particle being one of them. Okay, so the numbers for an alpha particle are 4 and 2, because what an alpha particle really is, okay, is that it's 2 protons, right, that have a mass of 1 and a charge of 1, and 2 neutrons, which has a mass of 1 and no charge. Okay, so we got 2 of each of these, so the mass is going to be equal to 4, and the charge is going to be equal to 2. So we kind of have to know these numbers for an alpha particle. Well, if 2 protons and 2 neutrons come off of the nucleus, then this is no longer uranium. It's a different element, because remember, the identity of the element is based on the number of protons. And if we have 2 protons coming off, it's going to no longer be uranium. Okay, so we got to figure out what it's going to be. And this is just where we have the law of conservation of matter. Okay, so on the left-hand side of the equation, we have a mass of 238. But on the right, we only have a mass of 4. So where does the other mass come from? Well, we need a mass of 234 plus the 4 that we have over here to equal what's on the left-hand side of 238. Okay? Now we do the same thing on the bottom. On the left-hand side of the arrow, we have a charge of 92. Okay? On the right-hand side, we only have 2. So we need another 90 to come from some other place. Okay? And that's going to be the element, okay, that's remaining after a chunk of the nucleus comes off. So we look up what atomic number 90 is. I look on my periodic table up here, and it says the symbol of Th, which is thorium. Okay, so uranium, when it loses an alpha particle, will become thorium-234. Now, this doesn't mean that this is stable. It isn't. Okay, its atomic number is above 90 as well. Okay. So there might be a series of alpha decays that take place until we get underneath the atomic number of 84. So we're in 83 or below to make the nucleus stable from a point of view of not having too many protons. So in this video, we're just covering what we call alpha decay. And alpha decay is a reaction that we write for when a nucleus is unstable because it has too many protons. A chunk comes off called an alpha particle, and when that chunk comes off, you create a new element. Okay, in this case, it's going to be thorium-234. The next couple videos are going to be talking about what happens when our proton to neutron ratio is different, or when there's too much energy. So if you found this video interesting, please give it a like and subscribe, and follow to the next video where we talk about what happens when the proton to neutron ratio is off.